So last bit from me before lunch on the first session. And I'm just going to give you some advantages and limitations to using Earth observation. But it'll have an environment focused because the project is looking at mapping habitats in particular. And it's also where most of my work area is, so it's my comfort zone, if you like. Earth observation is used for a wide variety of things for environmental monitoring, including some of these things. And it may not be as simple as just visualizing the data. One of the benefits of a GIS and spatial data in general is it can be used as input into modeling. So you could combine lots of different types of data sets, whether that's data on population, migration routes, anything like that. Combined with satellite data, you can input it into models and create outputs that are much more powerful than if you didn't have satellite data at all. So those are just an example of some of the things that I think in Earth observation in particular are very, very important for providing information either already or potentially in the future. So remote sensing does provide evidence. So if you've got the in situ data, then that massively increases the potential of this data set for giving you evidence base for what you need. And why do you need an evidence base? Because you need to make decisions on what you do in terms of land use management, where you build new houses, where you don't build new houses, where you can and cannot go, maybe even where you send your tourists, where you don't send your tourists, like the South Georgia example. If you've got evidence and you've got facts in front of you, it makes it a lot easier for you to make those decisions. And I think that's one of the key things of spatial data in general, but remote sensing in particular, especially when you see pictures like that. It's quite a powerful tool on its own, pretty pictures, so to speak. But like I said, you can't do it on its own. So that's when Neil went in South Georgia to collect his ground truthing data. And you can see that you can't go very far on foot. But collecting that amount of information alone does help when you create products because the satellite data does the rest for you. So it's all about integration of existing data sets and harmonization and how to get the most out of your data. And I'm not just talking about the satellite data here, but other data sets that you maintain and frequently update as well. It's all data management, not just focusing on Earth observation. And why is remote sensing key? Because you can look back through time, but you can also plan for the future because these missions are going to be frequently collecting data. So you're expecting data to be there, made available for you. So that is a powerful thing in itself because you don't have to plan, field trips or anything like that specifically. The image is going to be there. Regardless of whether you need it or not, it's there. And if a few months have passed and you want to go back and look at what that state was back 6, 8, 7 months ago, then you can go back and look at the image. So it gives you a powerful tool in terms of monitoring because it doesn't mean that you're missing out on information that you may have, missed if you were doing field data alone. But why do we use remote sensing in the environmental sector in particular? Because the environment is the sector that usually loses out to decisions. So going back to the evidence, the environment loses out because there is a lack of evidence. So there's a lack of understanding, not just by the people who do know about the landscape, but by the people who have to make the decisions as well. So if you can give them the evidence in a way that they can understand, and sometimes that is an image, then that makes some of those decisions easy to do from an environmental point of view because sustainability is what's going to be key for the future. If we destroy our environment, then it won't give its services to us anymore and we won't be able to live off the land like we've been doing. We know we can't maintain those levels of land use as we do now, so this sort of decision making is going to be even more critical in the future. And remote sensing, for me, I think is probably one of the most important data sets going into that, just because of that monitoring capability. So it's an important part of the toolbox, if you like. It's not the be-all and end-all, but it's a critical component of your decision-making future. So on to the limitations of satellite data. We've already touched a little bit on this, but it's just the surface. You can't see beneath tree canopies or caves or deep sea. It's literally what you can see on the surface from above. So if there's anything obscuring that view, you're not going to see anything below it. So another example of this is if you've got a diddle-dee, then you're not going to see the soil beneath the diddle-dee because the diddle-dee is on the top. That's the canopy. So that's what you're going to be measuring. The other major limitation to passive remote sensing satellite is the effect of the atmosphere. We want to be collecting data about what's happening at the surface, but unfortunately from space you've got that whole atmospheric column to remove before you can get to measurement on the surface. And there's ways of doing this, but as a community we've probably still not really nailed it. So we've still got some research and some work to do still on how to remove atmospheric effects from imagery, but we have some consistent ways of producing data sets, which I'll talk about in a second. Now the other limitation is the trade-offs you have to do. So I've already talked about MODIS data that goes over every day, but the spatial resolution of MODIS data is 1 kilometre squared. There's a lot happening within a 1 kilometre square that you're going to miss. But that's the trade-off you've got with the temporal frequency. Now, Sentinel-2 has made some inroads into that, so you've got 10-metre pixels, and in the Falklands and South Georgia going over it every other day, more or less. So we are getting there, but there is still a trade-off. And if you want very, very, very high spatial resolution, you're going to have to pay a lot of money for it. Either from space or you're paying somebody like Neil to go out and collect drone data for you. It's not something that's readily available. You have to plan and you have to spend money to get the data before you can do anything else. And then the other big limitation is the validation and the need for ground data to be able to do that validation. The lack of ground data is probably the biggest limitation we are facing now because we've kind of worked our way around the other limitations over time. So I think for Earth observation analysis to move forward and progress, we actually need to work on what we've got going on the ground in terms of systems to be able to validate those products. So looking back at specifically the atmospheric interference, this is a list of some of what we call pre-processing techniques that you need an expert in remote sensing data to do on your behalf. A lot of the free data sets do these three for you: the georeferencing, the orthorectification, and the radiometric correction. But what a lot of them don't do is this atmospheric correction. And some of them might do topographic, but that's the one that usually gets ticked off the list. So in South Georgia, for example, that would be a critical one to do just because of the topography and the illumination issues that Sally's already pointed at earlier. But there's a light at the end of the tunnel, so to speak. So this is Sentinel-2 data. So this is the amount of data that goes over in one day for Sentinel-2. And this is not being corrected for atmosphere, and this one has. So you can see even on the screen here, the difference in this one's a bit hazy because it still has the information of the atmosphere still in the image. And this one's a lot clearer because that's been removed. But what we're calling data that has all of the pre-processing being applied to it is analysis-ready data. So in the UK, we at JNCC and the DEFRA Earth Observation Centre of Excellence in general are one of the first people in the world to start using this term. And it's kind of exploded. So lots of people are now using it, and it's an established term in the community. The Australians have picked up on it in particular, and eventually NASA, USGS, and the European Space Agency started using the term. So USGS for Landsat were already producing what we now call analysis-ready data to a degree, but they weren't using the term. So we have agreed on the terminology at least, even if we haven't agreed on the methods to produce analysis-ready data itself. So I'm a firm believer in doing this at a national scale, just because you've got better digital terrain models available at a national scale, which may not necessarily be open data. But we have access to one in the UK, for example, but it's not open. So we can't make that open to anybody in the public. So we can use it to create a better data set, especially for the topographic correction. And I was using the South Georgia digital terrain model to correct for the South Georgia imagery I provided for the project. But that data is not available for the satellite providers to make their analysis-ready data better for your area. So I'm a firm believer in making a product that's suitable for your nation or region or whatever your the scale that you want to work at. But the European Space Agency do make this data available globally, but it has issues with it because it's done using global scale data sets, so it doesn't have the better information included in the process. So unless you're really desperate, I wouldn't recommend using it. Unless you understand the confidence and the evaluation that they provide and understand the limitations of that. But I would recommend paying somebody to, like us at JNCC, to give you satellite data. Well, it's not paying, I'm actually doing it for no cost in the UK for any agency at the moment, and I've been doing it for SARI for this project, and everybody has access to that data. So you might not necessarily need to pay somebody if you have somebody like me who's nice and kind and will provide you some data if I get something in return. But that's not money. And generally that could mean, you know, seeing a project being successful if the data is provided. That's my low criteria for success, if you like. I'm more than willing to do that.
Sorry to interrupt. I was just going to ask, with this is atmospheric correction.
Yeah.
Okay. So what is it about the atmosphere that you're actually correcting for?
So
temperature?
all of it, not temperature, so the particulates, and it's about how light interact with the particulates in the atmosphere.
Okay.
So water vapour is something that's corrected for, and then the atmospheric depth itself, so how much light can penetrate without being attenuated by particulates in the atmosphere. So what we do is model the atmospheric surface at the time that the image was acquired and remove those effects. So you're basically removing data that was acquired initially. So the values that you get here will be less than you get here because we've removed some data that were essentially atmospheric noise, let's call it that.
Okay.
Yeah.
So your correction factor for Falklands is going to be different for
Yes,
UK.
exactly.
Okay.
Because your atmospheric column is completely different, or it might not be, it might be very, very similar, but you need to know what that is. And then you need to apply that specific set of parameters to the model to get the atmospheric correction that's most suitable for your area, which is why I'm an advocate of doing it at a much smaller scale as opposed to doing it on a global scale.
Okay. Sorry, just another question.
Yeah?
About what you're actually removing there. Is what you've removed, is that actually valuable information as well? If you're into monitoring the atmosphere, then yeah. There's not a lot of applications that use this sort of data for that because there are other sensors that monitor what goes on in the atmosphere. But it is high resolution. So if you're wanting, you know, high spatial resolution and atmospheric information, then there are some cases where people do that, but it's mostly for research-based analysis at the moment. I don't know of any operational or application that actually uses this sort of data for monitoring atmospheric effects yet. They mostly go to the specific missions that do that and just that. So, yeah, you could, but it's probably not the best way to do it. So I've touched about this probably throughout the morning, but it is important to understand the scale that you want to work on. So this purple feature here, if you're interested to see if it's there or not there, then maybe the course data is just what you need. And perhaps, you know, you need the daily data to understand when it was removed, whatever that purple feature is to you. Because you need to know exactly from one day to the next when it was there and when it wasn't. So you could go to the course data. If you're interested to see what's going on within that feature, then you kind of need the higher resolution data. But if you really want to know how the extent of that has changed, then you need the very high resolution data. So that gives you a visual representation of the kinds of scale that are available to you, and it all depends on the application. So you really need to consider what's best and what the trade-offs are for your application. And I'm going to be asking you I'm going to give you some scenarios, and I'm going to ask you to make up what you think is the best resolutions for those scenarios later. So this is why I'm bringing this up again. So last but not least, we've already touched a little bit about this, but one of the biggest limitations of satellite data is the volumes of data. So the Copernicus program alone submits 8 terabytes of satellite data every day. So that's globally, mind, but you can imagine what it's like to try and manage those types of data volumes. And then if you're wanting to do something with those data volumes analytically, then you're going to have to find a way to access that data set. You don't really want to download that data, because downloading 8 terabytes of data anywhere in the world is a massive ask, regardless of what your bandwidth limitations are.
So 90 gigabytes in.
Yeah, but it would be a stretch. It would be a stretch in the places that are well connected too, with high fiber optic cables and whatever. So you don't really want to be doing that. So one of the ways of solving that problem is doing stuff in the cloud, storing everything in the cloud, moving your processes to the data in the cloud, because it means you don't have to move terabytes of data from one place to the other, and all you're actually wanting is the information from that data. And the information from that data is inevitably going to be much smaller in size and volume. So it's a smarter way of dealing with the limitation of satellite data. Now, the reason I'm showing you this is because in the UK we're building our own, just because the available platforms out there don't quite do everything we want it to do. The most common platforms are Amazon, AWS, Microsoft Azure, and things like Google Earth Engine, specifically for satellite data. But Google have other platforms that allow you to do stuff that don't have satellite data in them. A lot of the satellite archives are already stored on those platforms, but in its raw format, so not analysis-ready data. So we're using an open source architecture called GeoNode or GeoServer to build our own platform. And it does things like, so if you're only interested in a very small area, but you want several images of that one small area, then you can cookie cut that area. And I thought cookie cutting was just a term to make it more relatable, but that's actually the GIS term to actually apply this sort of tool. It's actually called cookie cutting. So even though it's got nothing to do with food. So we can apply that to our service, but it also allows you to download the images via web map service. So you get to visualize the data without downloading the data in your GIS of choice or platform of choice. But it also allows you to do fancy stuff like using an API to extract information. It allows you to spin off virtual machines in the cloud to do your analysis and lots of fancy stuff like that. At the moment, it's England only, but I am pushing for UK and possibly even overseas territories for Sentinel-1 and 2 data, possibly Landsat in the future. So watch this space. I'm fighting for you, for you to have access to this sort of service. And then all you need is, you don't even need a decent internet connection to use the virtual machine, but you probably need a decent internet connection to use the web services. But the platform itself, you can search and visualize things without a proper bandwidth, but if you wanted to download, then obviously you're going to need some bandwidth for that. But these are some of the tools that are now available out there in the world to try and counter the limitation of volumes of data that we've got. And it's not just satellite data, it's all sorts of other data sets too that are rapidly growing, but we have no real way of disseminating that information without having to go to the conglomerates like Amazon to store it on our behalf. So now I'm going to give you some scenarios. So I'm going to give you a requirement. I'm going to start easy. But all I want you to consider, so I don't want you to give me names of sensors or anything like that. I want you to tell me if you want coarse resolution, high resolution, or very high resolution satellite data.
if you think, you know, cloud is going to be an issue, then maybe we can look at using an active sensor for that. So the spectral resolution, do you only need to see something in the visible, or do you need the near infrared, the short infrared, if you're doing something with vegetation, for example? And then, how often do you need the image? So if you're, for example, if you're just doing one baseline, then maybe you just need one image. But actually, to get the separation of habitats, if you're doing maps, then you might need an image a season to try and capture the separability. So those are the answers that I'm looking for, not specific sensors. So I think I'm going to split you into groups. Was it groups of 4 or 5? 4. So if you can split yourselves into groups of 4, and I'm going to give you some scenarios.